In this section, we're going to talk about weak bases. We talked earlier about weak bases. They need to have some extra electrons, so that way the proton can be accepted by those electrons. So many bases tend to have nitrogens on them. So nitrogens like to have one pair of of electrons. So ammonia looking like this. Now oxygen also has electrons on it, but oxygen tends to be more electronegative, which means that it really likes to hog electrons. So it's not one for sharing or wanting to give its electrons up for from another proton. So while it can accept a proton, it doesn't do so as well as a nitrogen would. So compounds with nitrogen tend to be better weak bases. So just like weak acids, weak bases also have an equilibrium constant, Kb, and they work the exact same way as with weak acids we learned about in the previous section. Any other bases that have nitrogens but are not ammonia, so they have other carbon groups off the side of them, they are called amines. So we'll see here's methylamine with this blue nitrogen and a methyl group, a CH3 group off the side. And then here's hydroxylamine with an OH group off the side. So bases use their lone pairs to take a hydrogen. So here is ammonia reacting with water, and then it will take on a hydrogen to become ammonium ion, that's aqueous, and then water is left as hydroxide ion. So the two types of bases are basically those neutral substances that have a lone pair of electrons, like we talked about with the amines and ammonia, and also the conjugate bases of the weak acids. They are the anions because weak acids being neutral, when they lose a proton, they become anions. So, if I have HA going to H plus and A minus, this is my acid. Well, this is the anion of the acid, so that's the conjugate base. It can go in reverse and produce HA again, reacting with water. So that is just showing how our conjugate bases can act like bases, right, and produce our weak acids, and then also hydroxide when they interact with water. Here are various equilibrium values for our KBs for our bases. This one's not in order, so you can see our strongest one is methylamine, being times 10 to the negative 4. Carbonate ion, producing bicarbonate, is also a pretty strong weak base. And then we have something like ammonia and so on. So all of their conjugate acids just have an extra proton on them. And all of them, you notice, have a lone pair of electrons where they can accept a hydrogen. So let's practice. Let's do a problem where we have a 0.15 molar solution of ammonia. We're going to find the pH. So this is very similar to what we did before with our weak acids, but notice we don't have a hydrogen ion in this equation, we have a hydroxide. So what we're able to do is find, instead of hydrogen ion concentration, we find hydroxide, then we can find POH and then go to pH. So a little extra step there. So I'm going to do an ice table where I have 0.15 molar of ammonia. I have no products, and we don't worry about water because it's liquid. Then I'm going to minus X from my reactants and add it to my products. So at equilibrium, I have 0.15 minus X of ammonia and X of my products. So now we need to do a Kb expression, which will be my conjugate acid times hydroxide over the weak base. And we can look on our table earlier, the Kb value for ammonia is 1.8 times 10 to the negative 5. So that's going to be equal to X squared divided by 0.15 minus X. But because our initial concentration, 0.15, is more than 1,000 times larger than my Kb, I don't have to write the minus X. So that's cool. So let's find x. I'm going to multiply by 0.15 on both sides. And then I'm going to square root it. So x, which is equal to my hydroxide concentration, is equal to 1.6 times 10 to the negative third molar. So now I can take the negative log of that, which will give me my POH. So let's take the negative log of that value, and I get 2.78. So then we can do 14 minus POH is the pH. So 14 minus 2.78 equals 11.22. And that is my pH of my solution, which is basic, which is what we would expect. So let's practice again. Now we have a similar situation where I have ammonia in water, but the concentration is 2.5 millimolar. So first of all, that might catch you off guard. So 2.5 millimolar, we want to get that in molar. So if I have a milliliter or a milligram, that means I have 1,000 milligrams in a gram. So I have 1,000 millimolar in 1 molar. So basically I just divide by 1,000, I get 2.5 times 10 to the negative third molar. So if I have ammonia reacting with water to go to ammonium and hydroxide, now I have 2.5 times 10 to the negative 3 molar. For my reactant, no products. So when I do minus x and plus x, so the key difference here is we have such a smaller concentration to start out with that when we look at the Kb, which is 1.8 times 10 to the negative fifth, that number is much, much closer to that initial concentration. So it's not, we won't be able to do that approximation. So let's plug in now. So I'm going to have x squared on top and then 2.5 times 10 to the negative third minus x on bottom. So I'm going to multiply both sides by 2.5 times 10 to the negative third minus x and distribute in. And the bottom will go away. So we have x squared equals 1.8 times 10 to the negative fifth times 2.5 times 10 to the negative third is 4.5 times 10 to the negative 8. And we'll have minus 1.8 times 10 to the negative 5x. And so I can move those over. So I'll get x squared plus 1.8 times 10 to the negative 5x minus 4.5 times 10 to the negative 8 equals 0. And we'll put it into our quadratic formula. When we do this, we get that x equals two values. 2.03 times 10 to the negative 4 and negative 2.21 times 10 to the negative 4. Both those would be molar. So that one doesn't work because it's negative. So we have x, which is equal to hydroxide concentration, is 2.03 times 10 to the negative 4. So then I can do negative log of that to get POH, and that equals 3.69. So pH equals 14 minus POH, which equals 10.31. That's the pH. Okay, so now we have a solution made by adding sodium hypochlorite to 2 liters of solution, and it has a pH of 10.5. So calculate the number of moles of sodium chlorate in the water. So this one is a little bit trickier because we have sodium. So let's just write that out. So we have basically hypochlorite reacting with water to form hypochlorous acid plus hydroxide. So now we're trying to find out what's the concentration of this basically that we have. And we know the pH equals 10.50. So we can find the hydroxide concentration. We know that initially we didn't have any products, and we need to find the change. So POH equals 14 minus 10.5. So that is 3.50. So then I can find hydroxide concentration by doing 10 to the negative POH, which is 10 to the negative 3.50. So that gives me a concentration of 3.16 times 10 to the negative 4 molar. So that's what this is for hydroxide, and also the hypochlorite. 3.16 times 10 to the negative 4. So that's what that changes for both of these, and also the change on the other side. So we're going to have to subtract 3.16 times 10 to the negative 4. So here I'll have x minus 3.16 times 10 to the negative 4. So normally we don't know the change and we know of our initial, but here we don't know the initial of our base and we know the change. So hypochlorite, we can go back on the chart and find its Kb. So let's just write the Kb of the expression. We have hypochlorous acid times hydroxide over hypochlorite. Oops, not 3. And that Kb, if we look on the chart, is 3.3 times 10 to the negative 7. We'll have equals 3.16 times 10 to the negative 4, and we'll be squaring those over x minus 3.116 times 10 to the negative 4. So I'm going to multiply both of the bottom over, so I'll multiply x minus 3.16 times 10 to the negative 4 up here. And I'll get 3, it's getting kind of messy, I'll go to the side. 3.3 times 10 to the negative 7x minus 1.04 times 10 to the negative 10 equals, and then we'll do 3.16 times 10 to the negative 4 squared is equal to 9.99 times 10 to the negative 8. Okay, so now I'm going to subtract that over minus 1.04 times 10 to the negative 10. And we'll take that answer and divide by 3.3 times 10 to the negative 7. I just actually did this whole thing in my calculator in one step, putting the top part in parentheses and then dividing by the denominator. And that gives me x equals 0.324. 3024, and that will be in molar. So then it wants to know how many moles we put in, and so I'm going to need to remember molar is mole per liter, so I'll need to multiply by 2 liters, and I'll get 0.6048 moles of sodium hypochlorite. Okay, what's the molarity of an aqueous ammonia solution that has a pH of 11.17? So very similar, we're trying to find the molarity of my base, my weak base. I know I started out with 0 of my product, and I know my pH. So pH equals 11.17. So POH, because I have hydroxide, so I want that POH, is 14 minus 11.17. And that gives me a POH of 2.83. So my OH concentration is 10 to the negative POH, which is 10 to the negative 2.83, which is 1.48 times 10 to the negative third. So that is my hydroxide concentration. That's my ammonium concentration, since they're a 1-to-1 ratio, and that's also my change. So I'm gonna here and put that up here. So those will be added. But that's also my change in the negative direction here. So I am at equilibrium will have x minus 1.48 times 10 to the negative third. So ammonia, we know it's Kb, is ammonium times hydroxide over ammonia. And its Kb value is 1.8 times 10 to the negative fifth. That will equal 1.48 times 10 to the negative third squared divided by x minus 1.48 times 10 to the negative third. So once again, we'll move our denominator up here. We'll multiply on both sides, x minus 1.48 times 10 to the negative third. So that will go away. And we'll get 1.8 times 10 to the negative fifth x when I distribute that in. And I'm going to do that one minus, we'll do 1.8 times 10 to the negative fifth times 1.48 times 10 to the negative third. And that gives me 2.66 times 10 to the negative 8 equals 1.48 times 10 to the negative third squared, which is 2.19 times 10 to the negative 6. Okay, so now we'll move this over. We'll add 2.66 times 10 to the negative 8 to both sides. And then we'll divide that whole thing by 1.8 times 10 to the negative fifth. We'll get x equals 0.123 molar is what I started out with up here. Okay, so those are a couple different ways that we could approach ice tables in general, but in this case specifically referring to weak bases.